So today's lecture will be a completely different topic than before. So we are switching from Python to Fortran. And specifically also, I will mention that we are talking about modern Fortran here. So the material will be based on Fortran 90 and above the standard. So Fortran 77 is something you have to explore on your own. But so we start with Fortran. If you know Fortran, you can probably go back and learn the specifics of Fortran 77 as well. I will also go through some of the ways of how you can compile and use your get an environment where you can build your own software and do the assignments. So, okay, so with Fortran, you have to start with some history. So Fortran is one of the oldest programming languages ever. So if we look at the history here, the first version of Fortran was developed already in 1954. And it has a long tradition of standardizing its language. So we have Fortran standards like Fortran 66, 77, and we had a major update with Fortran 90, which was largely backwards compatible with the older Fortran standards. There was a short attempt of creating a Fortran language F that was not backwards compatible, but it was kind of skipping backwards compatibility is always a bad idea. Then we had a minor update in 95, and then we have had Fortran 2003, 2008, and 2018. So during this time, the language has developed significantly. So if you look at the modern Fortran standard today, it's a complete modern language. So it has modular structure. You have modern concepts like free-form text files. You have object-oriented development support. There is also array matrix handling, which I will show you later on in the lecture, making it a very nice language for numerical computing. So just to kind of show you an example of, this is a Pascal program. You can see the structure of Pascal program here. You have variables are declared in the beginning. You have begin and end to mark blocks of code. And you have nice readable code. So this is an example of just to show you some of the other languages implementing the same code. And this is the same code in C++, or in C. You have, instead of begin and end, you have brackets, but it's basically the same as Pascal code. So going backwards in time, this is the Fortran code as it was in 54. So this is basically how you wrote your code at that point in time. And this was actually a very big step up, because most of the numerical codes developed before this was done in pure machine code. And because there was a lot of machines at the time, different architectures, there was a need to kind of find a way to write numerical codes without actually doing machine code. And the biggest step was the, let's see here. Biggest step was actually the possibility to write expressions like this. This was kind of the big thing that made it useful. You also had if statements and stuff like that, but you still have this line numbering and go to statements and kind of pretty simple syntaxes. So the do loops, in the do loops, you actually have to specify line numbers for where things are, where you iterate and where you exit the loop and so on. So it was kind of simple in that sense, but it was a big step forward. Next step, this is Fortran 1. Here we got also function definitions, formatting statements, which made it possible to format your output in a structured way. A continue statement here to kind of end the loops. Here are some other developments. Here you have, I skip it. This is just a Fortran 4. I don't see any big things here. The big things came with Fortran 66. You have the do continue, you have Fortran straight and the right statements. The do loops were simplified, so now you only have to specify the line number 10 here for the continuation statement. And then Fortran 77, you get if, else, end if constructors. And the big step came with Fortran 1995. So now there is no line numbers. So this is just line numbers in that sense that to show the code here. But basically, you could write your code in free-form text format without the requirements of having line numbers. So now you have program, end program, you have subroutine, end subroutine. Quite more modern way of writing Fortran code. I will go through all these kind of extensions here. So, as I told you before, one of the important things about the later Fortran standard is you can use free form of the source. Basically, you can write anywhere in your in the text file, and you can compile that. So before that, you had only something called a fixed form, and that was inherited from the punch card era of programming. So certain positions of the file were for line numbers. So here you say that line numbers is from 2 to 5, and code is position 7 to 72. And actually, for the standard, you couldn't write code more than 72 because everything else was kind of discarded. Also, comments could be made by placing a character in position 1 of the source code file. There's also possibility to continue to the next line by placing a character at position 6 in the source code file. So imagine when you get Fortran 90, now all of a sudden you can write any kind of source code in a text file. So in this case here, the max line length is 132. But most compilers today can handle more, but the standard says it maximum is 132 characters. Comments is done by using an exclamation mark, and you can place that anywhere on a line. You can continue another line by using the and sign. And you can also have multiple statements per line by specifying a semicolon between the statements. So that is kind of a big jump in the way you present your code or write your code. So this is the way you write your code. So you start all your programs by specifying program, your program name. And in Fortran, you always declare your variables in the beginning of your code. I will get back to that later. So there's compared to Python, where you can kind of create a variable on the fly wherever you want in your code. In Fortran, all variables has to be placed in the beginning of your program block, beginning of your subroutine declaration, in the beginning of your module block. So you can't kind of, in the middle of your code, invent another variable. It has to be declared already. And here you can see you have the comment statement here. You can place that after a statement. This is the comment statement here. And can be used here to continue to the next line. So this here is a single statement continued by the and character. Here you have write, and you have another write here, which is, so I have a semicolon here, so you can write two statements after each other here in that sense. The basic program structure in your code is program name. Then you have your specification statements, your executable statements. So they have to be in order. You can't mix specification and executable, as I said before. You have a contain section where you can put other subroutines in your main program. And you can only have one main file that contains the program and program. So this is kind of the main program of your software file or software project. And also the only thing that is required in a Fortran code actually to be a legal Fortran program is end. So all the other things you see here is optional. So program name is optional. You don't have to do any specification statement. The contain section is optional. You don't have to do any subroutines. You also don't have to do the end program name here, but it's customary that you do those things. But the only thing required is end. So how do you compile and run Fortran code? So I will try to cover first from command line up to using Qt Creator here. So first is, what is a program? So up to now we have been running Python, and Python interprets every source code file line by line and interprets the line and executes that code. It has an intermediate format called a PyC file, which is the source code file compiled to tokens, but it still executes line by line. When we compile a Fortran code or create a Fortran code, the executable code is actually machine code that is runnable directly on the processor. And that machine code links with system libraries or your own libraries to interact with the operating system. So you can have links to your system libraries and you can have links to your own libraries. So together that makes your program. So you can create programs in multiple ways. So you can, of course, you can hand code machine code. That is hard. The next step up for that is you writing assembler source code files and compiling that source code to machine code. It's a little less hard, but it's still hard. Or you can use a compiler like Fortran, C, C++, and I have the higher language that compiles to machine code. So using a Fortran compiler, it will compile to machine code, and you can run it. And in Python, then you have you compile every line and executes every line directly. So in Fortran, you compile everything to machine code. In Python, you compile line by line, execute every line separately. That also makes Python more dynamic. In Fortran code is you compile it and it's done. You can't kind of execute things out of order in a command line interface. So how do we make an executable that you can run on your own computer or the Lunar systems? So you have to start with writing source code. Like in Python, you write a Py file, but for Fortran, you write an f.90 file. And you take those source code files and you compile them to something called object files. And object files are unlinked machine code. So basically, these are machine code instructions for your program, but they have openings or connections for calls to runtime libraries or operating system things, but those are not kind of finalized yet. And when you have compiled everything to object code, you use something called a linker to combine all these object files to a single executable and resolve all these links to the operating system so that they can be called correctly, or links to your own libraries as well. So this is the main process in images. So you have your source code files here on the left. And when you run your compiler, it creates object codes like this. So you have a corresponding file name, but with a .o extension, which can contain your machine code. You have some libraries. It's the .su file you can find on Linux and Mac. That stands for shared objects. Those are dynamically loaded when you run your executable, but you need to kind of specify them when you link together here. On Windows, those are usually called DLL files, so dynamic link libraries. And then you use the linker to kind of create the executable here, which is a standalone program that you can run on your processor. That doesn't require any Fortran compiler or any other tools. It's a standalone machine code program that you can run on your machine. That machine code is, of course, platform dependent. So if you have compiled on Windows, you can't take that executable and run it on Linux, and vice versa. On the same thing with Mac, you can't take a Mac binary and run it on Windows. So the source code is platform independent, but your executable will always be platform dependent. So if you look at, if you're running on Aurora, you can use the module system to load your software. So in this case here, I call the ML command here for module load, free open source software compiler toolchain. 2019, so the slide's a bit old. You can do 2020A today. And when you do that, you get all this stuff loaded. So you have your GCC compilers, you have your libraries here. And if we do Fortran here, which is the Fortran compiler, -- version, you get the version of the compiler. So in this case, this is 8.2.0. So we write our source code using the F90 extension. You can write some other extensions as well, but this works for any standard app. So it's not only for Fortran 90, it also works for F22, 2003, and so on. So if you want to compile Fortran source code to an object file, you can use Fortran -C, which stands for compile, and then your source code file, and that will generate a mysource.o. And you can compile multiple source code files to multiple object files by just adding more file names to the command line tool. And if you want to link the code, you can do Fortran, and then you specify the object files here, and it will generate an executable a.out, which is a default if you don't specify any name. If you want to specify a specific name of your executable, you can do Fortran mysource.o and -o for output, and then the name of your executable that you want to create. And that will generate myexec as an executable. Fortran actually has a way of simplifying this. So you can actually do this entire process in a single step. So if you do Fortran mysource.f90 -o myexec, the Fortran compiler will automatically create an object file and link and create an executable. You can also add multiple source files to your command line to create an application from several source code files in one go. So that will do both the linking step, or compile step, and the linking step in one single step, which can be convenient if you want to compile something. So I wanted to show how that can be done. So I have here a command line. Now this is a Windows computer. Just gonna make that a bit larger here. So I have here a source code file, mysource.f90, and I can do. First, I want to just do the object files. I can do Fortran -C mysource.f90. And now you can see that I have a mysource.o here. So this compiled to an object file mysource.o. And I can compile that again. And then I just take my mysource.o -o test fort like that. And now you see it created a test Fortran executable, which I can run from my command line. And the syntax is exactly the same on Linux, except for that on Linux, your executable will not have the .exe extension. I can also do, so I can do Fortran directly, mysource f90 -o test for 2. That will do both of these things in a single step. And now I have a test for 2.exe here as well. So you can do both of these things at the same time. I will also show you how you can use Qt Creator. So I have provided, let's see here, some extensions for Qt Creator which you can use to compile Fortran code. And the Qt Creator, which you can download actually on Windows, contains the Fortran compiler, so you can get that automatically. And if you want to create a new project here, you create new file or project in Qt Creator. You select non-Qt project here is important here, a plain Fortran application. You click choose, and then you can choose where you want to put them. I do the test Fortran 1. Next. Keep the settings here. CMake is something I will go through on the next lecture, but this is a build system that we will use for this course. Then we have to choose on Windows here. You have a lot of environment here. For the Windows, you should choose the MSys environment to build your software code or your Fortran code. Finish, and that will create a simple Fortran program here, which is you can compile. And you can see here that it created the source code files here, main.f90, and you gave it the name test41. You have a make list file here for the build instructions. You can select which version you want to build here. So you have you can build a debug version, which is useful when you debug your code. You can also build a release version, which actually switches on the optimizations and builds the optimized version of your code. To build your code, you can use the hammer, and you can click on compile output here to see what it does. You actually see the compile statements. Then you can press the play here to actually run your code. You see it started up a command line tool, and you see it said hello Fortran here, so it actually worked. If you want to add source code files to your project, you can do that as well. So you can do, let's see here, new file, and then you select Fortran here, and you can select an empty source code file or a module file. So we take a source code file here, and we say test.mysource. What happens now is if you save that, and then you have to run CMake again, and you see here that it added your source code file again. So you need to kind of check the build, run the build system again. I think it will do that automatically when you run as well. And then you can press play here to execute the code. It's also possible to debug your code using Qt Creator. So you can create a breakpoint by clicking here on the left side, and then you press the debug play flag here. And now you see it will stop here on line 13, waiting for execution. You can also see here on the right side, you have the variables that are declared. So argc is the argument coming into the code. It has value 1. And then you can continue running the code. Let's see here where I have my. So there's a small toolbar here where you can do continue here to continue the execution. And the code exited here. So let's see if I have hello Fortran here. So this is the way you work on compiling your code on Windows, on Mac, and Linux. Qt Creator is also available on the Aurora system, so you can run there as well with Qt Creator. So let's start from the beginning and go through some of the concepts of variable or the programming constructs of Fortran. So we start with the variables. In Python, you don't have to declare variables are kind of defined when you create them. This is not so in Fortran. You have to declare all your variables to kind of use them. And the naming is you can use 1 to 31 characters, alphanumeric characters, letters, numbers, and underscore. You can have variable names that consist of both uppercase and lowercase characters. However, variable names are insensitive. So uppercase A is equivalent to a lowercase a variable. So there is no difference in, it's a case insensitive language. Also, the first character can't be a number. So you can't have a variable starting with a number. So valid variable names are here. You have A A underscore thing is okay, X1 is okay, mass is okay, Q123 is okay. You can have time of flight with 2 underscores. What is not okay is 1A, that because it starts with a number, A thing, because there is a space, and you can't only have one single non-alphanumeric character. So most of the things work as you expect. There are some different variable types built in. So the basic ones are integers for integers. You have real, which is floating point numbers. You have complex for complex numbers, logical for Boolean variables, character for strings and characters. There is also a special derived data type which you can use to define your own data types, but it's not the built-in ones. Declaration is done by this. You have a declare type, and then you have double colon and the variable you declare. You can also specify a number of different attributes that kind of specify what kind of variable it is on other properties of your variable, and you give that before the colon declaration. So here are some example declarations. So here you say this is an integer variable, and then you have colon, and then you can specify a list of variables that should be integer. So you can have A, and you can have multiple ones with separated by commas. Here you have a real variable, B, a logical as a Boolean variable, flag. Arrays are declared by specifying the dimensions after the variable name. So in this D parenthesis, this is a one-dimensional array, two-dimensional array, 20 by 20. Those are fixed and pre-allocated before execution. It's also possible to declare arrays by using the dimension attribute here. So integer dimension 10, and then you can have C, D, E, and F. So all of these variables will have the dimension 10. You can also declare a single character variable, basically something that contains a character, single character, that is character. You can declare an array of characters, dimension 60. This is not a string, it's an array of character, which you can't handle in the same way as strings. Strings are declared by specifying a character and then the length here, and then the name of the string here. You can create an array of strings by specifying this is a string of 80, and then you have 60 lines with strings that are 80 characters long. Sometimes you want constants that don't change during program execution, and that is done by specifying the attribute parameter in your variable declaration. And you also have to specify the initial value of your constant. So in this case, I have an integer constant, we specify with parameter, and I specify a equals to 5. So a is now a constant that can't change during the program execution. You can use that in declarations like this, but they are fixed during the execution of the code. Another thing that is really important in Fortran is variable precision. So up till now we have just declared integer, real, and logical. We have not specified what that actually means in precision, how many bytes the floating point consists of, or stuff like that. So by default, the standard, if you just put real, it will take the smallest precision of real, so to save memory, so to speak. So if you don't give anything, just put real, it will be a real consisting of 4 bytes, a single precision real. The problem is that in Fortran, because Fortran runs on so many different platforms, the actual precision is difficult to specify in a machine-independent way. So Fortran has 2 special statement function that you can actually use to query this from the system, so that you get the actual precision, because the specifier you can add to your declarations can be different on different architectures. I have also a question about parameters need to be declared before they are used in further declarations. Yes, they have to, in the same way as for variables, they have to be declared in the beginning of your subroutine or beginning of your program. So to be able to specify precision in a machine-independent way, you can use the two functions, selected real kind and selected int kind. And those are not normal functions in that way. You can only use these functions in a constant declaration. So for example, if you can give the precision of a data type real by specifying a number in parentheses after the variable type, and then you specify the variable name, a real 4. The problem is that for most of the time, for example, on x86 platforms, 8 and 4 are actually the bytes for the number of the number of bytes you use for the floating point declaration for the data type. So in this case, the first case, real would be an 8-byte floating point as the double in C++. Real 4 will be a float in C++, 4 bytes. But the thing is that is only valid on the Intel platform. So there are some other platforms that don't necessarily have this, have different precisions in the floating point definitions. And what you can do then is use the selected real kind to get define a constant that you can use to declare the variables, and you are guaranteed to get the kind of precisions you require. So in this case here, I declare integer parameter, AP will be my constant I will use, and then I assign this constant selected real kind 15,300. That will define the precision in a non-platform way, and we'll get back to what they mean. And then you can use real. You can specify kind equals to AP. We can also do real AP directly here, and those variables will use this precision specifier. And you will be guaranteed that you get the precision you want. So what does it mean? So 15 is the significant decimals you want to be able to represent, and the 300 is the mantissa that you want to, the range of this. So it can represent numbers from minus 10 raised to the 300 and 10 raised to the 300 here. So this way you can actually exactly specify. There is no confusion on what the precision will be. Important thing with this is also that when you declare scalar values in your code, you actually need to specify the precision of those as well, because Fortran has too long heritage back to be backwards compatible. And if you just specify a scalar decimal value in your code, Fortran tries to minimize the space it requires to store this variable, and will use single precision for that scalar constant. So to be able to specify scalar values in your source code with enough precision, you need to actually add, in this case it should say AP here, but okay. You have to specify the precision as a postfix to your suffix to your scalar values. So just to illustrate this is a code that declares the pi constant twice. So I have declared two variables here with the precision 15,300. So they are declared as real AP, P1, P2. So if I declare pi1 equals to 3.1459 and so on, but without the suffix, and the pi2 with the suffix here. And if you just run this code, you get the result as below here. So you see that you have 3.1459, and then it falls apart on the first one here. So this one is actually the scalar value in your source code is stored in a single precision floating point value, which kind of is not what you expect, and it's a very easy mistake to do. And in the second part here, you actually specify this suffix here, and then you get all the decimals in the pi correct. So this is an important observation that you need to kind of think about when you write scalar constants in your code, that you need to specify the suffix here is really important. Another thing that is left over from old backwards compatibility is something called the general type rule. And that has been part of Fortran for a long time, and means that you don't have to define variables, declare variable data types in Fortran by default. They are defined implicitly by Fortran. So variables starting with I to 9 to n are always integer if you don't say anything. All other variables are real by default. And this is something that you want to avoid in your code, because you would want to be very specific when you declare variables. And what you can do then to kind of make sure that everything is, you have to declare everything, you add a directive in the beginning of your program called implicit none. It tells the compiler that you have to check for that every variable is declared and the general type rule is not used. Yes. You assign variables by using the equal sign, similar to Python. You see here I have a suffix here again. You have integers, same thing. If you assign true or false variable in Boolean, you use a keyword called .false or .true. Characters can be assigned. Character strings can be assigned by using a single apostrophe or double quotes. It works both other ways. So it's similar to Python here. If you want to use a single quote in a string, you can use double quotes around the string, and vice versa. If you want to use a double quote inside a string, you use single quotes around the string. Also, an important distinction with Python, a variable that is declared but never assigned is considered undefined. So you can never assume that a variable is 0, for example, if you just have declared it. What happens is that the program will, the Fortran will allocate a memory location for that variable, but until it has been assigned, it just points to some empty memory location in your computer that can be anything. So if you just declare the speed variable here and do nothing with it, it's considered undefined. And the general rule is that you shouldn't refer to undefined variables. It's completely legal to refer to an undefined variable, but you get an unexpected result if you do. And when you assign a variable, it's considered defined. So if your speed is assigned 42, it will be defined. And you can in this case, it's safe for it to be referenced by other expressions or functions and so on. Also, an array is also said to be defined when you have when all elements in the array have been assigned. It's considered defined. If you only assign one variable to an array, it's not defined, it's undefined. And with arrays, it's especially important because if you allocate an array using dynamic memory allocation later on, it will point to some space in memory, and it will contain the garbage or the things that are at that location in memory, and not 0 like you perhaps would expect. Operators, you have the common one. So you have a power to operator, which is a double star. Multiplication is a star. A division is what you expect, a slash, plus and minus. So it's very similar to what you have in other languages. This is the order of operations, also what you expect. Relational operators, you have two kinds of these. So the left column here is the Fortran 90 and above. So these were added to the Fortran above, and otherwise you have these numeric character operators here. That is .lt for less than, .le for less than or equal to. And the reasons for this alphanumeric operators is because the older Fortran didn't allow for special characters like these here. So that's why they had to solve that in some way. But it's still available. It's still completely legal to use those. Logical operators, you have to use dot and or dot, not dot, and so on. And if you do integer expressions, result divisions will be truncated to 0, towards 0. So 6 divided by 3 is 2, 8 by 3 divided by 3 is 2, and so on. And there are some things here. So if you do integers with the power operator, you will need to kind of consider this here. This will be 0. So 2 raised to minus 3 will actually be 0. So if you want to do this, you have to do floating point data types to get a result on that one. If you mix data types in expressions with different data types, the weaker data type, so for example, an integer is weaker than float, will be converted to the stronger one. So an integer will be converted to the stronger of the two types. So in this case here, you have a times I, and a is a real, I is an integer. In this case, I will be real. You can also use arrays in expressions. So many of the operations you can do on normal data types will also apply to arrays. So if you use operators between arrays, you can actually do. They will operate on the elements. So if you add two arrays together in an expression, it will do additions element-wise through this array. And also the order operations of these kind of operations is not specified in the standard. So you can, if you optimize your code, it can try to optimize these operations to work well on a multiple cores on a shared memory machine, for example. So here are some examples here. I have arrays here, A and B, which are 10 by 20. And I have B here as a vector here, one-dimensional. So if you do A divided by B, it will actually execute, divide every element in A, comma J divided by I, comma J in B. So this is similar to what the functionality you have in MATLAB or in NumPy. So you can do multiple operations in a single expression. And the second example here, we have a V, and we add a scalar value 1 to V. And what happens then is it will actually add every element in V 1.0. You can also do 5 divided by V. So this will be 5 will be divided with a new array here, which is every element is 5 divided by VI. And then you can add another, do an index operation here where we get back to, which will add those values in the completed operation to a single array. It's also possible to do a comparison of two arrays. So if you do A dot equals dot B, it will be true if all the elements are the same in both of these arrays. So it will actually loop through and compare, and if all of them are true, it will return true, or if some of them are not true, it will exit. So I will see if I can show you an example of that. That was example 8. So here are some examples here. Here I also have what you can do is in Fortran is if you have an array and you do an assignment operations like this, it will assign all values in A to 20.0. And here in this case, if we want to specify a single element in the array, you just specify row and column equals to the value. And the important thing is to note also indexing in Fortran by default starts at 1. I also have a question here. Operational array work only if the sizes match. In Fortran, arrays must be identical in size to be able to do these operations. You can do it if you have different size. You can do an index reference to get the same shape out of a different size array, but the result of that operation must be the same size as the other one, the other left side operator, so to speak. Here I also have B, which is also an array. I assign that to 2, V equals to 2, and then I execute all of these expressions here. So let's see what happens when we run this. Now, because this project contains a lot of examples, it has to compile all of them before we can run our code. So please be patient here. I didn't have a print statement here, but we can try to run it in debug mode here. Just to see here. So now on the left side here, it's a bit small here to see, but we can see and we can see the values here. Also, you can see here that we have a lot of garbage here in the variables. So if we step one step further here, step over, now you see here that A was assigned 20 here. So all of the values in the array was assigned. And we look at A, now we assign column 1 and row 1 to 2. So let's see, we step over here. And you see here it's also 2 now. You can actually see the rows here as well in A. But in Qt Creator is mostly done for C. So the debugger is kind of C-ware. So it will start arrays with 0 here, but it's actually the array 1 here. So let's step through this and see what happens. And you can see that B now also was assigned 2, so that is also okay. If we look at the results here, EX1, run that, so it should be the division of A and B. And it seems to be that, so 1, 2 divided by 2, it should be okay. So, and so on. So it's very powerful syntax here that you can use for your, instead of writing loop. In many other languages, you have to do loops to do all of these expressions. But in Fortran 19 and above, those are available as built into the language. So I will make a short break now, and I think we will be back at 1:15. Okay, so let's continue. So next, we'll go through one very important part of Fortran is the array and matrix handling. Arrays and matrices are basically the same. There is no distinction with the data types in Fortran. So everything is a single array data type. Yeah, arrays and matrices are a very important concept in technical and scientific applications. It's a very efficient data type in Fortran. You can allocate them statically or dynamically. And there is also support for advanced indexing, slicing, and assignment of these arrays. We already started a bit about the array declarations. So you can declare them in different ways. So you can do first data type, and you use the same precision specifier as we discussed earlier. You can use the dimension attribute to declare several variables of the same dimensions. You can also specify the dimensions as parentheses after the variable name. Two-dimensional, comma between, and you have 6, and you can have multiple dimensions. So there is no restrictions on the number of dimensions you can define. In essence, arrays are only blocks of memory in the computer. So the indexing is just a way of jumping forward in the block of memory, so to speak. So every array in Fortran is a block of memory in your computer. You can, by default, array indexes, as I said before, starts with 1. That is if you don't redefine your indexes, which is also possible in Fortran. So you can declare, for example, the index variable here has indexes starting from -3 and going to 3. So here is also a difference from Python here. The end value is actually included in the indexing here. So in this case, you get an array that starts from -3 to 3. Note it will not contain the actual numbers here, but this is just the index in the array. Assignment is done by specifying rows and columns. So in this case, I want to assign row 5 and column 6, and I just assign a value to that specific position. You can assign the entire array by specifying, leaving out the index notation and just assigning a value. Then it will assign every element in the entire array that value. You can also, in a single line, for example, if you have vector one-dimensional arrays that contain certain numbers, you can do assign them in a single go. You don't have to specify the actual index every time. So in this case, you start your array assignment with a parenthesis slash, and then you list your values you want to assign, and end with a slash parenthesis here. So it can be quite practical if you have smaller arrays that you want to assign in a single go. You can use this kind of syntax here, instead of using v0 equals to 1, v1 equals to 2, and so on. You can also assign what's called slices, and that is a single column or row at a specific position in your array. So in this case here, I have 2 one-dimensional arrays B and C, which are 4 elements, and I have a 4x4 array A, and here I can take out slices of A and assign to these arrays. So in this case here, I have row 2 and all the columns. So this will in essence be row 2 I will assign to B. In this case here, I will assign column 1 all of the rows. So this is very similar to the MATLAB syntax for arrays. Let's see here if I can show you that example here. So here I have A equals to 0, so I zero out the array, and then I assign the columns in different ways here. I think I don't have to show that. I can skip that. It's also possible to combine these assignment operations in a single line. So for example, if you want to assign row number 5 a certain number of values, you can do that by using the colon notation and then using the parenthesis slash assignment here to assign multiple values to a single row here. That works also for columns, so you can mix and match that. And you can also assign an array like this values. Also, all arrays are stored in, as I said before, at this continuous locations in memory. So they're always a part of the same memory, allocated memory block. And two-dimensional arrays are stored column-wise in memory. So what does that mean? So for example, I have a single array with 16 elements. They're stored kind of continuous in memory. That is kind of logical. If you have an array that is 8 rows and 2 columns, the values are stored column-wise. So it starts going down the first column and the next column like this. So the numbers here correspond to the actual memory locations in memory of your computer. Same thing if you have a 2-row, 8-column array. It's stored 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So column-wise. This is different from NumPy's default storage scheme. So NumPy is implemented in C, and C stores the arrays row-wise. So it's the other way around. So if you want to exchange information, I will go through that on the mixed language lecture. You need to create your arrays in NumPy to match the storage of the Fortran code if you want to communicate between Python and Fortran. If you only use a single Python program or a single Fortran, you never have to kind of bother with this thing. You can just ignore it. But when you want to communicate between different programs, specifically if you communicate on a pointer level, so basically passing a reference to a memory location, you need to know how it's actually stored in that memory location. I had that before. So now we have done a lot of variables. There are other things that are important in program as well. So you have something called conditional statements, if statements, case statements, and so on. And so we start with the if statements. So the simplest form is you have a if, and then you have a logical or Boolean expression, and then directly after you can execute the statement. So that statement will be executed if the Boolean expression is true. You can have multiple statements that you want to execute if it's true in a code block. Then you use the then statement here after the Boolean expression, and then you have the code here will be executed if this expression is true. And you can also have nested if statements like this. So if the expression is true, then execute block 1. Otherwise, else if this expression is true, I execute this. Else this will be executed. So here's an example of this. You have you write enter the integer value here. So if x is greater than 1000, this will be executed. If x is less, this will be executed, and then you have if then else here to illustrate the use of nested multiple blocks in a single if statement. There's also a select statement. Please note also, you are required to have parentheses in your expressions here. So this is you can't leave that out. You always have to have a parenthesis in your Boolean expression in your if statement. Select statement. So select statement you can use if you have if you see in your code that you have a lot of simple if statements and you have a lot of them. It's probably easier to use a select statement to kind of make it more easy to read. So in this case, you have select, and then you have an expression here, and that is, for example, a variable or something. And then you have case statements here where you specify the value that if expression is certain value, it will execute this block. And you can have multiple of these after each other. There's also a possibility if you don't have for every kind of expression, you can have a default here that will be executed if none of the above case selectors are not fulfilled. It will execute the default block. So this is an example here. I enter a value here, select case value. So this is the value I want to test on. I can select here if it's greater than 1, if it's equal to 1, if it's between 2 to 9, if it's 10, if it's between 11 and 41, if it's 42, and if it's greater than 42. And this here will be executed if none of the above are executed. This will be executed here. So this shouldn't happen in this code here. Another important thing in code is to be able to repeat statements. So the most important one in Fortran is the do statement. It starts with a do, and then you have a loop variable, and then you have a start value, an end value, and then you end the loop with end do. You can also have, so when you run this, it will go through 1 to 10. It's also possible to have a step as the third parameter to the do loop, and then it will kind of increase the loop variable with this step value each time it iterates. Another important thing is that you are not allowed to modify the loop variable inside your do loop. That is not that's an illegal operation in Fortran. It could be that many compilers do that, but problem with if you rely on a compiler feature, it could be that when you move your code to another compiler, it will fail. So it's also important, for example, if you parallelize your code, that these variables are not changed in a way that the parallelization algorithm can't foresee. So don't do that. I think the compiler will complain. So let's see here. I have example 11. Yeah. Also, you can control the loop using as two statements. So you have, if you want to get out of the loop and continue execution after the loop, there is a exit statement you can use that will go out and continue execution after the loop. So it's a way of quickly terminating a loop under certain conditions. There's also a way of, it's similar to what you have in Python called continue. So in Python, it's break and continue. Here is exit and cycle will continue to the next iteration. So that's a way of kind of quickly continue to the next iteration without going through a lot of the other code in your loop. However, you need to be somewhat careful with this kind of construct because it can lead to hard to read code if you have a lot of these exit and cycle things in a loop, in a single loop. So here I have an example of simple loops where I just print out stuff. And we can see here if we compile. So the first one just iterates from 1 to 10 and do 2 to 30. And we can try here to see what happens if I try to change the loop variable here. So if I just go I equals to 2. So you see here, you can't compile that code. So the compile will fail. So it says here, I can't be redefined inside a loop. So this is an illegal statement. So we'll remove that directly. And here you can see I loop from 1 to 1,000, and if it's greater than 50, I will exit the loop. So this loop should never go to 1,000. It should go to 50. And if we run this, So you can see here that if less than 20, it will cycle. So it will go back here. And if it's larger than 20, it will just print out I here. So it continues here. And then if greater than 50, it will exit. So you can see here that it controls the code like that. It's also possible to have a iteration with a condition. So that statement is called do while. And then you have a logical expression which is evaluated every loop. And that, if that evaluation is true, it will continue to execute the statement in here. And that is typical when you want to iterate something until some limit is reached. This is a typical loop here. So in this case, here have if x is less than 1.05, it will continue to print out the sinus function and increase the x counter here with 0.0 and 0.1 every time. So, and you see here, it will stop here 1.10, and it's less than 1.05. So that is, it will not go to the next iteration here. It will go. It will continue one step further from this one here, and then this is not fulfilled, and it will not execute that once more. Built-in functions. So, to be honest, Python has a lot more built-in function than Fortran. There is a lot of functions built into Fortran as well, but it's not. It's very focused on functionality, numerics, and I/O and stuff like that. So, but there is a lot of them anyway. Mathematical functions. So, of course, you have all the normal mathematical functions available. And the nice thing with all of these functions is that they also work in arrays. So, if you have an array, you can use that to compute the sinus of every value inside an array. So you don't have to have a special, like in NumPy, you need to use the NumPy, special NumPy functions to do this. In Fortran, all of the functions in Fortran can handle arrays as well. Conversion functions will convert to two different data types. So in this case, abs A will return absolute value A. A_int will truncate the floating point value. And if you have a floating point value and you need to get an integer, you use the int function. You can round a floating point to the nearest integer. You can convert an integer to a real using the real function. You can also, there's a max function here which will return, if you have multiple values in the call, it will return the max of these values. There are some matrix functions as well you can use. So if you want to compute the scalar product, you can do dot_product. There's a built-in matrix multiplication. It's called matmul. And also you have a transpose function to transpose a matrix. So there are no built-in operators to do matrix multiplication, but there is functions to do it. So this is what you can do there. Let's see if I have a good example for that. So here I have an example here where I declare a lot of variables here, and I fill them with random values, and I print them out, and then I do a matrix multiplication here. And it's here it's very important that all the data types and array sizes are the same, as I said before. So if you want to do matrix multiplication that returns in that a value is to a certain size, the left side of the assignment must be that size. So in this case, I have a matrix multiplication by two matrices 10 by 10. The result will also be 10 by 10. So C here must also be fit here. Otherwise, you get memory errors, which is not what you want. Dot product here, I have two vectors here that is multiplied here to a dp vector. So let's see here. So here we have matrix A is 10 by 10, matrix B is 10 by 10, and here is the resulting operation C. And here you have two matrices here, and the scalar product will be 0. So they are kind of 90 degrees, so you see that works. Yeah, as I said before, you can use functions operator with arrays. I already illustrated. So in this case here, I have 3 arrays, 20 by 20, and I can C equals to A divided by B, and then C can also be the square root of A, and that means that square root of A is a square root of all the elements in A. Just to illustrate a more concrete example here for my own area, structural mechanics, I will do a simple stiffness matrix here. So in this case, I want to compute the stiffness matrix KE, and that is done by multiplying GTK element and this operation here. I want to do that in Fortran. Those are also, so G is this one here, and then K element here is this expression, and then I have some variables here I want to compute as well. So the Fortran implementation can look something like this. I declare my variables here. I use my precision operator here to make sure that I get the correct precision. Declare my arrays here, 2 by 2, 6 by 6, 2 by 6. Compute all my scalar values here. Make sure that I have the suffix RK here. Compute my length here by using the square roots here and the power operators, the nx, ny, and nz values. I want to try to make sure that I don't do too much computation inside arrays, and also only do the computation once at a single place for efficiency. So then I assign my KEL, the first row, and I use this assignment declaration here with parenthesis slash to kind of quickly assign the 2 values on a single row. Same thing here, 2 by colon, the second row, like that. And I multiply here KEL with the scalar variables E, A, and divided by L. This multiplication here will be element-wise, so all the elements in KEL will be multiplied with this one here and assigned to the final matrix KEL. Then I create my J matrix here by using the same assignment operators here and the second row like that. Also, I always try to keep my precision suffix here, so make sure that the precision what inside my matrix here is okay. Just go one moment, please.